No problem if you guys allow me. Okay.
Sounds good.
And there were some good questions that came up last time, so it was good to. It will be mostly elementary geometry of conic sections, how it relates to, and but I think it is worth doing because often we spent a lot of time in the derivations, and then analysis is you spend less time on the analysis. So I think let's just do that. So I need to. Oh, before that, logistics. So where is midterm 2? So can I make all the homeworks due on Tuesday? You guys think you can make it?
This Tuesday, have everything turned in. Is that what you're saying?
Yeah. Yeah. By the exam, so that you guys also get off with it.
Yeah, I can try. I'm like really not doing great, but yeah.
Yeah, I mean, this is just to push you guys. Not that I really want you to take this too seriously. Don't stress out on it. You can always relax it. But if there is a deadline, you guys will put an extra effort. Otherwise, it will be the week before the exams. Then you will all panic, and that's when you will do the same thing. So we try to push you guys. But again, if there's something important, very pressing on your end, this doesn't have to take priority. Okay, with that, this is midterm. First, let's say midterm 2, but before that, I wanted to say homework, right? So homework, all homeworks, all due April 14th. Okay, everything is due on 14th. I haven't posted a homework today from Tuesday. Then the point is that then I can also have a very good assessment of a grade on Tuesday. If the homeworks are not there, then your grades are not really a true representation of where you stand. But that's not the purpose. The main purpose I feel is that I want to push you guys a little. But again, don't panic. So midterm 2 on April 14th, which is a Tuesday. It has not yet been uploaded, but I plan to upload it during the by the end of the weekend. I think that's when it will happen, and it will be due by the end of Tuesday, but or let's say by end of due by Thursday, let's say, so that since I'm making the homeworks due, you guys have a little more time on it. So due on April 15th, Wednesday. Okay, so its official date is this, but you can make it due on Wednesday. Is there anything else I have to tell you? Can I have a class on Tuesday? Since it's going to be take home, and all the questions will be available to you as a take home. No one question.
Yes.
Yeah.
During the exam. Okay. So I'll have.
Did you not say we're running behind?
Yes, that is the purpose.
Yeah.
So I would like to have the class, but then I don't want to disturb. You guys will be all involved in the exam and homework, so I think we can have a class on Tuesday. Okay, so I think that will help. Anything else you can think of with the exam and any questions?
No, I think
Yes.
that's good.
You already gave us a breakdown of what to expect on the exam, right?
Oh, you would like to have a breakdown? Is that
It'd
fine?
be nice to know kind of what.
Okay, that's a good point. Let me quickly, since I'm in front of my computer, I can quickly try to tell you guys. I haven't made the question. I know one question that I'm going to put into it. That's concerning the gears that I pointed out. The 2 gears, there was an extra credit problem. Okay, so there will be a problem on a small angle approximation. That's homework 5. Yeah, so I think what you can expect is there will be one problem. So this is exam, right? So midterm 3. So one of them will be
Midterm 2?
Huh?
Midterm 2, not 3?
Oh yeah, midterm 2 because this is graduate law. Yeah, thank you. Midterm 2. There'll be one problem on small angle approximation. I think there was a homework problem very similar to the homework problem, except that the initial conditions will be changed. I'll try to do something so that the numbers can be made simpler, but I never come up with a good configuration that gives a good number there. Okay, so
I think number 2 in homework was kind of hard to find. Had lots of root 2s floating around.
Yes, so that is how it will be. I have noticed that I have not been able to come up with the right initial conditions that will get rid of those root 2s. So I couldn't help it. Okay.
Okay.
Yeah, if you guys can come up with one of those problems with having all the richness of the problem and at the same time not having all these root 2s, that would be nice. I think it should be possible, but I not spend too much time either.
I think if we can make the terms inside of the square root to be perfect square, then it would be easier.
Yeah, I couldn't. That's what I'm trying to say. Okay. I'll try to. I would like to. Okay. But I don't promise. It will be on gears. So I'll construct a Lagrangian for this system where the 2 gears perfectly rolling. Okay. So and now that we have so then there is stationary. So there is Noether's theorem. So we did rotations, translations in space and translations in time. I can add on to this maybe a virial theorem. That's typically that I do. I can add, but it depends on what I would do. Okay. So this is on homework 5. So this is related to homework 5. This is related to homework 6. That's related to homework 7. And since we have done a good bit of Kepler problem now, we can do one on Kepler problem. So that's, ideally speaking, I would like to talk, or whatever I said, the gear problem is there in my head. I have to just type it. This will be pretty much the same as your homework problem, except I might change the coefficients as I was telling. I would like to make them perfect squares. Noether's theorem, maybe the virial theorem. You have heard about the virial theorem, I think. Have you guys heard of virial theorem?
No, I don't think so.
No. What is virial theorem? Virial theorem says that it's very much used in astronomy a lot. It says that often in classical mechanics, the average of the kinetic energy is exactly equal to the average of the potential energy. Kind of problem, which is not always necessary. So in what situations, so under what symmetry does that work? And if I get it right, I think it is, if it is a central force, then you will always have the average of a kinetic energy to be equal to average of the potential energy. So that's a symmetry. So under what? Sorry, that's a statement. And under what situations does it give? That's the connection with the Noether's theorem. Okay, and that's something I can ask. And Kepler problem. What I'm going to do today is do the ellipse. Do a lot of details for the ellipse. Maybe you guys can extend it for hyperbola, maybe, or parabola, or one of the problems related to what I'm going to do today. Like until yesterday, we derived the conic section. Today, we are going to analyze it. So I think these are relatively straightforward, but at the same time, often assumed that you all understand it. So I think it's a good exercise. Does it help?
Mm-hmm.
Okay.
Yes.
Okay, let's go back to Kepler problem. We pretty much brought down, we already used angular momentum conservation and other features of the problem, and eventually brought it down to a motion in a plane. And we said that the Lagrangian for that is r dot phi dot, and that's half mu r dot square plus half mu r square phi dot square, and then minus the potential energy. Potential energy is already negative, so it's plus g m1 m2 over r. So I think historically, probably the most well-studied problem we can say in all of science. If you take the whole of 500 or actually more, right? I mean, if you bring in the whole of astronomy, it is the oldest well-studied or well-written subject. Like it goes back all the way to 3,000, no, 5,000, right? You can say three. We have written.
It starts with ancient
people
Egypt.
knowing about it. Yes, Avinash?
It starts with ancient Egypt.
Yes, exactly. So it goes all the way 3000 BC, I think, BC. So it's about 5,000 years. But only since, I would say, since Newton, we really started working on the details of it. So still, even since Newton, I think it is a pretty big deal. And it is, I think, the most well-studied topic for good reasons, right? That's what goes around us. Okay. And we said that we showed last time that, or first let me write down the equation, right? So this corresponds to the equation of motion. Mu r double dot is equal to, well, so it is r, right? So it is mu r phi dot. So it is mu r phi dot square and minus g m1 m2 over r square. And so that was the equation of motion. We worked on that a little, but what was more important was that we identified the Hamiltonian and we said that was conserved, right? So we said there was a total energy which is conserved, and that was half mu r dot square plus the potential energy, plus the potential energy is Lz square over 2 mu 1 over R squared and minus G M1 M2 over R. Right? And I should define my LZ here. LZ was derivative of this. That is mu R squared phi dot is LZ. Okay. And this piece here was also defined as U effective. So it is effectively, if you think of radial direction to be, you're interested in the motion in the radial direction, then this is an effective potential. In fact, the radial the acceleration due to the motion in the phi direction has been included as a force, right? Centrifugal force in there. Okay. If you were to plot this, we last time did this. So if you were to plot this, this corresponds to this is with respect to R, and that's U effective. Like the effective potential unknown, not the total energy, that's the effective potential unknown. And somewhere here is a minimum. And did we evaluate that minimum? I think we took the derivative, we took the...
I think we did.
Yeah, we did that. And R naught we calculated was equal to, or
LZ
how much
square
we
over
stressed on it. Tell that again.
LZ square over mu G M1 M2.
Yes, that sounds right. LZ square over
Mu R naught cubed.
mu G1.
That's so it's mu
G
G1
M1
M1 M2. Yeah.
Yeah. Factor of 2? No, because 2 cancels out when you take the derivative. Yeah, you're good. Yeah, that's R naught, right? And accordingly, at that, so that sets a scale for R. And similarly, at that point, at that minimal point, there is a potential that sets the scale for energy. That's a special energy, or it's a very natural units for energy. And how much was that? So U effective or not. So if I were to evaluate the energy at that point, how much does that come out to? Can you guys calculate and tell me quickly?
We just have to substitute R naught into R square, right?
Yeah. Can you do that? Yeah. So U effective or not? Probably change the zoom. So that's equal to LZ square over 2 mu R naught square minus G M1 M2 over R naught. Correct?
Mm-hmm.
But I can process this a little. Can I simplify this a little? So that's also equal to.
Well, LZ square.
Go ahead. I was going to do, so this is also LZ square over, that's a vector of half mu G1 G M1 M2 times G M1 M2 over R naught square, right? And minus of G M1 M2 over R naught. Right? That's nothing but R naught itself. That cancels away one of the R naught, right? Which then gives you a factor of.
Shouldn't you have isn't LZ squared equal to GM1 M2 over or GM1 M2 R naught?
That's correct, and mu also, right? Exactly. So you can do that also. LZ square is mu times G1 M1 M2. Yes, exactly. That's what I'm doing, but I'm doing it in a weird way. Yeah.
Okay.
No, you're correct. What I'm replacing is LZ square to be replaced with in terms of R naught, correct? That's what
Okay.
you're saying?
Mm-hmm.
So this is nothing but R naught. So one of the R naught cancels out, and maybe what you are in whatever way you are saying it is more transparent. But that's what you get, correct?
Mm-hmm.
And that's exactly minus half of G
GM1 M2 R naught.
over R naught. Okay. What that means is that, notice this was the sum of two potentials, right? If you had done this, like this, that was your 1 over R potential, correct? Or GM1 over R2. Right exactly at R naught, the effective, the gravitational potential is somewhere here. That's half of that is where the effective potential is. That's where the stable point is at R naught. It's exactly half the energy. Okay, that's what it means. But the point is that this is minus half of that. So let's remember that. So it's minus half of G M1 M2 over R naught. So it's a negative quantity, and it is exactly half of the potential, gravitational potential at that point. Okay, that's your two scales. And if you allow me to erase this, is that clear? Shall I, for the space, shall I erase that?
Yeah, you can.
Okay, Avinash. So, let's look.
I was just speaking into a muted computer.
Have it again.
I was just speaking to a muted computer.
I think I didn't get it, but
He was just saying that he was saying yes, but he was speaking while his mic was muted. So
I see. Yeah. Okay, so that's some of the constants we need to work with, right? So that's, again, in any problem, we need a units. So this is a very natural set of units. You measure distances in the units of R naught, which is the point where this potential is a minimum, and energy will be measured in this units. And our solution, we solved these equations and we got our solution as R of phi is equal to, so there was this in our numerator, we had, we wrote some constant C in there, correct? From last time. Let me recollect. Or not. Yeah, let me write the solution the following way. One step back, and we had our solution as LZ over R is equal. Do you guys remember what did we write for solution with all the constants?
Mu G1 GM1 M2 over 2LZ. I'm just looking at my notes.
Yeah, just from your note. Yeah.
So it is mu GM1 M2 over 2LZ
And then
minus C cosine phi minus phi naught. So C is, well, C squared is 2 mu E plus mu g m1 m2 over 2lz squared. 2lz to the whole square.
Yeah, so let's first get that c squared. So c squared was 2 mu e plus, if I,
Plus mu g m1 m2 over 2lz, and that term squared.
lz.
2lz. 2lz.
And the
Yes.
whole square.
And then that whole thing squared.
The whole thing squared, yes. Check.
Because you said c squared was equal to 2me in the first term. And then you said, you know, you still had the term mg, or mu g m1 m2 over 2lz minus s squared.
Okay. Do you guys all have your notes with you from last time?
Yes.
Can you go back a few steps and check for this factor of half? Not close to this, all the way back. I think right when we, as
I didn't have that 2 in there. Just a few steps back, I didn't have 2, and somehow mysteriously it appeared.
Yeah, I didn't either. I actually had 2me plus, or 2 mu e plus mu g m1 m2 over lz times
yes,
s
that's what it should be.
minus
So
s
somewhere I
squared.
think I started writing 2 down there.
Yes, after that we wrote 2, and somehow it appeared out of nowhere.
Is that clear? It is appearing from nowhere, so it is a mistake rather than, is there any concept? There is no,
I don't see where it would have come from, no.
okay, good, okay. Is it okay to just blindly get rid of this 2 at this stage?
Yeah.
Okay, because I was checking on it and it's not there. I went to the video and looked at it and it just suddenly shows up. Okay, is that clear? Or should I go through this where exactly it went? Okay. But that will be going a little. We'll lose some time there. So if you allow me, this is just see. This is to be corrected in the earlier notes. Okay, that's what's your c squared. Okay, that was just a copying error. Nothing conceptually went wrong. Okay.
So in the term r phi, we shouldn't have a 2 either.
No, that's the point.
The 2 lz squared
2
term.
square should be there. Wherever there's a c square has this definition.
Okay.
Okay, so now let me write r phi.
In my notes, that 2 shows up in the R naught as well, which it shouldn't.
R naught is this. This is the definition of R naught, and it will stay there.
Right.
That's
Yeah,
it shows up there also. Yeah, it shouldn't show up. Yes.
Yeah.
Yeah. Good point. Okay. Is that clear? Should I go back a few steps and clarify
No,
that?
we're good. We're good.
Okay. And R of phi comes out to, again, can you remind me, how did we define this?
lz squared over mu g m1 m2.
In the numerator? So R of phi,
Okay, if you just want to do that, you can do r naught over 1 minus c cosine. Or e
so
cosine.
does it come out to be R naught over
1 minus.
1?
We said 1 minus, but we determined that 1
Yeah,
minus.
let's stick to minus. Let's stick to minus. Okay. 1 minus, this is C. Did we get C?
C cosine phi, yeah.
C cosine phi minus 1. Okay.
I thought we got E. I thought we got E in there. So E replaced as CLZ.
I was just going to work on that because I did this again in the morning today, and this should come out dimensionless unless this is dimensionless. I don't think this is dimensionless. 2 mu times E, right? So is this what we got for sure? Can you check?
That's what I wrote down, but because you have L, I think you just copied it wrong because you have LZ over R, which gives you
Yeah, let's write that
M1,
expression. I think I like that expression very much. If you help me write this, LZ over R, right?
which is equal to mu
And
G,
that's
mu
okay.
G M1 M2 over LZ minus C cosine phi minus phi naught.
Okay, fantastic. Right? This we all agree, I suppose, right? This is with the definition of C here, and this is now, I'm going to erase this, whatever we wrote for R. We're going to derive that from this one. Okay? Reasonable with the definition of C that we wrote just now. Let's divide out by LZ square. So this is 1 over R is equal to mu G M1 M2 over LZ square minus of C, which was square root, right? So this is square root of 2 mu E, and that is a cosine of phi minus phi naught. Agreed? When I'm going to divide by LZ, there is an LZ square that comes in the inside of the square root, and this was plus, right? Plus mu G M1 M2 over LZ. So this is our LZ square times. Is that correct? Agreed? Notice this become an LZ square now, because earlier it was LZ whole square. Now it is LZ square whole square, which is LZ raised to 4. And this is LZ square. With me? Which is the same as 1 over R naught, over notation. And now let me process this. What can I do? So this is surely mu G1, what was it? Mu G1 over LZ square is 1 over R naught, right? So it is 2. Can I do something here? So that is 1 over R naught. So it is 2 times E times why am I not able to do this? LZ square G M1 M2 divided by G M1 M2. So that's
Mu.
So that's G M1 M2, right? And there is an R naught. Is that correct? Of 1 over R naught square. I think that's correct. Which is the same as, pull out an R naught, 1 over R naught. So I had to pull out an, so this is the same as square root of 1 plus E over G M1 M2 over R naught, and there is a factor of 2 now. With me?
Yes.
Like basically all getting the dimension straight here, getting the scale of energy right where we want. R naught, I can put it in with R, and energy comes with the effective potential now. So this is 1 minus of, let me introduce a minus sign so that I can identify that with the effective potential, which is negative. So this is U effective at R naught. Right, so that's a dimensionless quantity. That's the idea that now we are measuring things in their own units, like natural set of units. So this is, energy will be measured in the units of this, so it will always be a number. Radius is measured in terms of R naught, so that will always be a number, and then that's the sign phi minus phi. Okay. We define.
Can you explain the minus again? The 1 minus?
What is effective potential? Yeah, it is right in the board.
Oh, okay.
There was a negative sign there, right? So
Mhm,
this is like effective potential is negative. So I introduced the effective potential. So it's a little confusing in the sense this is a negative number. So this is a negative of a negative number. So it's positive in principle. But then we haven't said anything about the energy E. That could also be negative.
Okay.
We'll discuss those things. Okay.
Okay.
So as of now, it seems like it is a negative quantity. So I'll try to clarify with magnitudes in there. But at this point, let me just define this to be E. This will turn out to be the eccentricity of the orbit, but that's just a parameter at this point. Okay. So our radius of phi. Oh, I might be off the. Okay, so R of phi is equal to R naught 1 minus E cosine of phi minus phi naught. Okay. We had some questions about what this phi naught means and what this negative sign means. Could that be, can this be negative or positive? Yes, it can be both negative or positive. Just to give you the answer, the point is if you have an ellipse, if it was an ellipse, and remember it could be a hyperbola also, and in hyperbola, it becomes necessary to choose that to be positive, but we will come to that. But if you have an ellipse, you can have your origin either at the left focal point or to the right focal point. Okay. If I choose it to be a negative sign, your origin is convenient at phi equal to 0, whatever condition you put, that leads to the origin being on the left side. If it is on the positive side, that is on the positive side. So let me clarify that. So let us say that, let us put an initial condition that R at phi equal to 0. So radius at phi equal to 0. Let us say it is here. I haven't said where this is. Let me say that my mass is somewhere here. Remember this is your phi. See, yeah, that's your phi, and that's your radius R. Let's say the mass is at phi equal to 0. It is at the farthest point from there. Oh, I should be careful here. I didn't say this right. I didn't draw the radius, right? So that's your ellipse. Hopefully it's clear that on the right side it is longer, and your focal. Oh, this is center if you want, and the focal point is down here. And let's say that's your angle phi. So notice your origin is on the focal point. I haven't defined what a focal point is. All that will come in as we go today. But with our little bit of knowledge about the ellipse, we know that something like this is going to show up. So let's say that at phi equal to 0, it is at the farthest point. And when will this be the maximum? When will the radius, the solution to this be a maximum? Look at this solution and think of when will that be a maximum? This will be a maximum when the denominator is a minimum.
Mm-hmm.
Like the denominator will be minimum, I think, when it is 1 minus e, right? When cosine phi is actually 1. Clear?
Mm-hmm.
Cosine can go from +1 to -1.
So
Is 1.
I see in that R phi, that looks like a reciprocal function to me. I don't see an ellipse at all. I'm confused.
Oh, we'll see that today. Yeah, that's one of the things that I'll do. We'll see that. As of now, it's not that. Yeah, agree.
Okay.
But I don't think of this as an ellipse that's going forward. This is just to bring in the idea of why this plus or minus sign. We'll come to there, okay? So as of now, let's say that R of 0, suppose I were to give you that this is equal to R naught over 1 minus E. Okay. We will notice that in a minute, or let's say in 10 minutes or so, I'll show that this is actually the maximum value of R, which is kind of obvious from the denominator itself. Okay. Is it an ellipse or not? We don't know that yet. But there is a maximum value for this radius, and that's R naught over 1 minus E. That's better?
Yes, because what I'm not seeing exactly is now when we go back to the definition of 1 plus 1, if it's
Yeah.
cosine, yeah, 1 plus E is different than 1 minus E.
Don't worry about it. As of now, let's
By a
proceed
factor.
and
Okay.
yeah, things will fall in place.
Okay.
Comes out reasonably clearly. As of now, this is R of 0. And let me put that as a condition. So this is equal to R naught and 1 minus E cosine of phi naught. And that immediately tells me that phi naught should be 0. Right? So this implies that phi naught is 0. That is just to set your phi naught. That is with this initial condition. I don't have to, if I don't give you that initial condition, that phi naught stays open. Okay, so let's stick with that initial condition. Okay, so our again, if I were to copy this down on the left hand side so that later I can use that space. I actually don't need my C. So the solution is R phi is R naught over 1 minus, notice I pointed out last time that it is positive, but it doesn't matter. And I also set R of 0 to be equal to R naught 1 minus. And there is a definition of E that is coming in here. Again, at this point, it is just a definition, but this will come out to be the eccentricity of the ellipse. Okay, with me. So let's, with that understanding, let's proceed. And first, let's ask graphically, what can we conclude? So let's, so again, let's go back here. What's your U effective as a function of R? And that's your reduced vector R. That's your R naught. And that's U effective or not. This is a negative number here, so that's 0. Okay. Notice in the when you're actually suppose Earth were just starting to form, there is an initial condition there. What are the conditions? One is that you set your R0, and R0 is decided by LZ square. So the angular momentum is a choice that you have. You can give whatever angular momentum you want to give to the system. And the second is velocity, which is basically the total energy. You can decide how much energy you want to give to the system by pretty much pushing it with a certain velocity. How much velocity do you give and how much angular momentum do you give? So which of course goes back to where you begin from and what's your initial velocity. That's your initial conditions. That pretty much boils down to setting your energy, and this is your potential energy, and total energy E is equal to, right, kinetic energy plus U effective. What is this? I just now said this is a kinetic energy. Is that correct? Is this the kinetic energy of the mass of Earth, let's say?
Of just Earth?
Uh-huh. Or Earth.
Why would it be a reduced
System.
mass if it was just Earth?
Sorry, of the reduced system, sorry, of the reduced mass. Is this the kinetic energy?
Well, we're missing an
I feel
angle.
like it's missing some.
Missing some. If a mass, think of this, if a mass mu is moving in a plane, what is its kinetic energy?
1/2 mv squared.
mv square. Is this velocity?
Mm-mm.
Yes or no?
You need
No.
Yeah, you need the
yeah,
angular coordinates
angular.
also,
Yeah.
right?
Mm-hmm.
So this is only the radial kinetic energy. So with that feature in mind, so this is the radial kinetic energy. This will come back again. So there shouldn't be any confusion on that. So radial kinetic energy plus the potential energy is a constant, right? That's a Hamiltonian, that's the energy. Energy of the system remains a constant in the Kepler problem. Okay? And we have a choice of this. What's the minimum value E can take? Is there a minimum value E can take?
Well, yeah. According to your graph, yeah.
No, this is not energy. Remember, this is potential energy.
Oh, yeah. Okay.
That's potential energy, right? U effective. E, is there a minimum value E can take?
It could be anything.
E could be anything. Try again.
Well, if the system was not moving, then the minimum energy would be the effective potential. We cannot go any.
Why is that?
And we cannot go any beyond that.
Why not?
Because if there are two masses, then that means there's some effective potential between those two.
Okay, so ask the question again, just so I can hear what you're asking.
Is there a bound on energy E? That's what I'm asking. Can I have the energy to be minus infinity, for example?
I don't think so.
And why not?
I don't know, but it just doesn't feel right.
Yeah, so the point is the kinetic energy is a positive quantity, right? K is positive. That means to say that K of R is greater than 0. That means E minus U effective has to be greater than 0. That means E has to be greater than, or let's say greater than or equal to, right? So energy has to be greater than the potential energy. That's what Avinash said. But the reason is this, right? Because kinetic energy is a positive quantity. This is a positive quantity. So energy cannot go further below than that. Okay? Which means that so energy is not in the scale. So but it's the same units. So this is your E is equal to 0. If energy was equal to 0, that's where it will stay. And that's only one point. If energy of the system was 0, total energy, then it cannot move in the sense this term, the radial kinetic energy has to be 0.
In that case,
Energy was equal to 0.
I'm sorry to interrupt. In that case, we would also be defining the U effective at R naught to be 0.
No, we said E is 0.
Yes.
Correct? That means these two together has to be equal to, no, that's not what I meant. Sorry, you're correct. Because E is not 0 here, right? That's this, the minimum value that I was thinking of. Sorry. Yeah. The minimum value is U effective or not. Sorry.
Yeah.
Which is a negative quantity, remember. This is a negative number, right? So the minimum value it can have is this value. Agreed? And if that was the case, at that point, effective energy cancels out. So what's the kinetic energy associated with the radial motion?
0.
0. Right? Radial motion, that's 0. That means to say that R doesn't change. Right? Kinetic energy radial means that R dot is equal to 0. That means R is equal to constant. Right? What's the motion corresponding to R equal to a constant?
Circular motion.
Circular motion, right? So if you fix your energy, very special energy, to be exactly the potential and effective potential energy, the motion will be circular. That means to say that this will stay here, right at the bottom, right? That's perfect circular motion. Right? So circular motion is a solution possible in conic sections, right? In the Kepler problem. Except that the energy has to be very fine-tuned. Clear? Any question there? So that's the first case we can have. So that's case 1, let's say. Of course, energy doesn't have to be at the minimum point. It can be further up. So somewhere here, energy is still less than 0. But now it is greater than U effective R naught. Right? And now
You change, you're going to the right, right? Your center changes location.
center changes location. What does that
Like
mean?
as you go up, the
Uh-huh.
you're changing the place of R naught changes, right?
No, R naught is the same. R naught remains the same. That's your minimum here.
But U effective changes. It's more like it still should be bound in the center, right?
It's bound on the center, but it can go anywhere here.
Mm-hmm.
The point is, since E is what is fixed, U effective, as you go up, U effective has decreased its negative value. So K has to increase.
Okay. Okay.
Right? Or sorry, did I say that? So since
No, I got you.
Right? So if you're at this corners, kinetic energy is 0. If you're here, kinetic energy has to be very large. because energy has to be fixed.
Mm-hmm.
Right? Think of harmonic oscillator, right? When it is right at the endpoints, it is 0. So if you start from the motion here, comes down very large velocity and comes back here. Right? But right on the tip here, energy is exactly, or energy is fixed here, then kinetic energy is equal to 0. That's what gives you the minimal value. So as you increase your kinetic energy, it goes further down. Is that clear?
Yes.
Right. Okay. So the negative values, positive values can be a little confusing. Maybe so the way to see it is that U effective at this point has a lesser negative value. If I were to add the kinetic energy to that, so then my total energy being fixed, that kinetic energy has to be more. Correct? Did I say this correct? But anyway, so I think let me not go through that too much. Any questions on that, by the way? I think the diagram is pretty clear.
No, it makes sense.
Okay. So the moment you say that, it is clear that there is a minimum value and there is a maximum value, right? This is a maximum value. We'll call it R max. And this is a minimum value. So if the energy is less than 0 and greater than that, it is bounded. The radius of the mass is bounded. Right? It cannot be more than a certain point. It cannot be less than a certain point. It's pretty much what moon does, right? I mean, it actually, moon has this, sometimes it's a little farther, sometimes it's a little closer. And of course, Earth also does the same thing. So it's closer and farther. Okay, that's, and we'll see that that's a equation of a ellipse. As you go further, so this will be the second case. This will be the ellipse. We haven't shown that yet. Third case is when E is exactly equal to 0. That's when you're right on this axis, right? What is the value of the R max when energy is equal to 0? So this maximum point keeps going, moves further, and it goes to infinity, right? So when energy is exactly equal to 0, there is a minimum point, but the maximum point is all the way equal to 0. In fact, if you further go up here, the same condition, if energy is greater than 0, so it's not bounded anymore on one side. On one side, it is not bounded. The other side, it is bounded. There is an R minimum still, but there is no R maximum. And that is what happens with the hyperbola. And this right boundary where E is equal to 0, that's a parabola. Again, it's not very obvious why I'm saying all this, but we'll see that as we proceed. Okay? And it's 2 minutes. Can I take more time today? Since you guys usually don't have.
Yes.
Yeah, we started.
Yes.
Too.
Do you have a class?
I have like 15 or 20 minutes.
Oh, you have only 15 or 20 minutes. Okay. So let's try to finish the ellipse at least. Okay. This discussion should be clear as of now. So let me proceed and let's work with the case when energy is negative and greater than the effective potential.
Did you say that it's a parabola only at E equals 0?
Only E equal to 0, yes.
So at E above 0, it's a hyperbola?
That's a hyperbola.
Gotcha.
It's a hyperbola.
Okay.
Okay. But why I mean, it's not obvious at this stage. Okay. What was that?
That's
From one of.
they're outside my house.
Okay.
Is that a fire truck?
No, it was a police car. I don't know what's going on.
So let's consider the scenario when energy is less than 0, a negative quantity, and U effective or not. That's our, remember this is a negative quantity, that's a half of G M1, M2 over R naught. Okay, that's our case, and let's immediately write, what can I do here? Yeah, so let's go back to our expression for energy. Expression for energy is half mu r dot square, that's your kinetic energy, plus your effective potential, correct? So effective potential was, if we remember correct, what was it? Effective, okay. Can I write this? Yeah, so this is plus Lz square over 2 mu r square minus G M1 M2 over R. And now let's ask for what R is R dot equal to 0. There are special points when this equation is satisfied and with velocity being 0. If you were to use this as a plot, in this plot, when does the velocity become 0? The velocity becomes 0 at these 2 points. They're called the turning points. Is that clear? Jordan, Avinash? Have we lost them?
Yes. Yes.
Okay. Sharon?
Sorry, I was muted. I was talking.
Oh, okay. Okay. Yeah.
I think you got me.
So,
Apologize.
yeah. So this is called turning points. Okay. Let's quickly get it in our units. So I will put R naught, right? So there is a factor of half, and I'll divide by R naught. This is G M1 M2 over R squared. Great. I think so. And minus of G M1 M2 over, let's say R naught here and R naught over R. I think that's a way to do it. Is there any better way? Let's see. I can also do this R squared. Yeah, I think that's the same way of saying it. This is equal to 0. I'm setting this equal to 0, and the first term can be written as R naught square over R square, and the second one can be written the other way. If I were to divide this out, I get E over G M1 M2 over R naught, the factor of half, that's your effective potential, that's your R naught over R the whole square, minus 2 times R naught over R. This quantity here, E over this E is already negative, so it is a negative quantity. So let me write this in terms of E squared. So remember, E over 1 minus of E times minus half G M1 M2 over R naught was your E squared. Right? I would put a negative sign in there, and then I can say, how do I set this up? So a positive quantity will be equal to E square minus 1. So this is E square minus 1 is equal with me. Yeah, okay, so that's a quadratic equation. Solve it. Did we lose someone? Oh, someone is wanting to come in. I think he left, maybe for office hours. Okay, plus I had to put this on the other side, plus 1 minus E squared. That's a quadratic equation that gives me some values for the turning points. Right? Let's evaluate that. The points are 2 plus or minus square root of 4, and then minus 4 times 1 minus E squared divided by 2. Right?
I see what's going on.
So this is 1 minus 1, so it's an E squared, so that's equal to 1 plus or minus E. Right? So there is a minimum value. So our minimum is equal to R naught over 1 plus E, and our maximum is equal to R naught over 1 minus E. Reasonable?
Yes.
So that's your two turning points. Okay. So now let's see further, and let me now use the other sideboard. Okay, what else can we learn from this? Still not an ellipse, right? We just know there's a maximum and a minimum. And let's go back to our equation, and like if you want, one can plot this and see, right? This is not much one can do. So this is 1 minus E cosine phi, right? We set phi not equal to 0. If you, in terms of polar coordinates, that is the equation of an ellipse. So in principle, we are just going to go from something more familiar, and that is rectangular coordinates. We know the equations of an ellipse in rectangular coordinates. So let's see how that comes by. So let's multiply this out. So that's
Okay. So when E is greater than 1,
when E is greater,
Hyperbola.
then that's different. That is hyperbola.
when E is greater than when energy is greater than 0, but your E value is greater than 1, then you have an ellipse, right?
No, E has to be less than 1 and greater than 0.
Yeah, less than 1 and greater than 0.
Less
Okay,
than 1 and
okay,
greater than
okay,
0.
Okay.
E is equal to 0 is a circle.
E is equal to 1 and E is equal to 0 is a parabola, right? And then
Exactly. Mhm.
and then E greater than 1, E
It's not.
the energy greater than 0 is a hyperbola. Okay.
That's,
Now it's
we'll get
making
it.
sense to me.
Yeah, that's exactly the classifications I want you guys to get into your head. But as of now, let me convince you about where are these parameters sitting on an ellipse equation. So this is x is equal to r cosine phi, y is equal to r sine phi. That's your rectangular coordinates. So we want to work in rectangular coordinates now instead of this polar coordinates. So this is r is equal to r naught plus e times x. Just wrote this onto the right hand side. Square this quantity. So that's r square. That's square of that. R square is nothing but x square plus y square. And r naught square plus e square x square plus 2 times e times r naught times x. Okay. I can, so remember your ellipse equation, we want to identify this as an ellipse. So this is 1 minus e square times x square and minus of 2 times e r naught times x plus y square is equal to r naught square. Okay. This is 1 minus e square. Okay, we'll do some manipulations here. This is x square minus 2 e r naught over 1 minus e square times x. Okay. Let me define a few variables here. So let's say this is r naught, or a, right? This will be your major axis, like in an ellipse equation, that is a major axis that comes in. So this is r naught over 1 minus e square. As a focal point, and just as of now, these are just variables. We will see that this will come out to be the focal point. So this is e times r naught over 1 minus e square. That is e times a naught, if you want. With those definitions, I have 1 minus e square I can say this is 2 times f, so I'm going to add and subtract x minus f square plus y square. I'm adding an f square there, so it is a 1 minus e square plus f square. Okay. This is equal to r naught square plus 1 minus e square. F square, remember, was e square r naught square divided by 1 minus e square whole square. One of the e square cancels out with that. Whatever remains, one of them cancels out, and this comes out to be exactly equal to r naught square divided by 1 minus e square. With me? Pull that all onto the right, or if I were to divide out by 1 minus e square, or you can bring that onto the left. This gives you the equation x minus f the whole square over a square, right? Because r naught over this is a square quantity, so there's a 1 minus e square also there, so that's a square plus y square over, I have to pretty much bring this down here. So there's a 1 minus e square. We define that as b. So y square over b square is equal to 1. Where b now is equal to r naught square over 1 minus e square. So b square is this. Okay, so that's why it is an ellipse. But where are these all these terms sitting together? Let's quickly draw a diagram. So if you were to have, so that's your ellipse. This is if you were doing rectangular coordinates, it's convenient to have this, but actually our center is somewhere here. Like we are at one of those focal points, and that's your R, and that's your angle phi. The maximum value here for the radius is this is R max. So this is R naught over 1 minus E. So that is this distance from the origin, which is we will see is the focal point, to that point. So let's say this was your A naught. This is your 2 times A. Suppose that was 2 times A. How would you calculate that? 2 times A would be the same as the maximum value R naught over 1 minus E. And the minimum value here is R naught over 1 plus E. So that's your, this is your R minimum. And that's your R maximum. Right. So R minimum plus R maximum is what is 2 times A. So that's 1 plus E. And that's exactly the 1 minus E and 1 plus E cancels out. And it is R naught, 2 times R naught, right? 2 times R naught over 1 minus E squared. So A comes out to be exactly R naught over 1 minus E squared. That's what we used for the coefficient A. So the total 2 times the major axis is nothing but the minimum distance and the maximum distance. Okay. And what about the focal length? Focal length is this point here. So this is the focal length. Yeah. How will you calculate the focal length? Focal length is, seems like, is A minus R minimum, correct? So A minus the focal length is A minus R minimum. A is R naught over 1 minus E squared minus of R minimum is R naught over 1 plus E, right? Which is the same as I can multiply by 1 minus E, so R naught minus R naught 1 minus E divided by 1 minus E squared. R naught cancels out, so it is E times R naught over 1 minus E squared, which is exactly E times A. So E is a fraction of the half major axis. So E is less than 1, so it will be smaller. For a hyperbola, it is outside. Right? E is larger, and so we can define a similar quantity there, and it will come out to be large. All that is good. Now, here's a question for you. So this is actually an orbit of an Earth, right? Earth's orbit is like this. So this is, I think,
Earth. Location Earth.
and Earth going around the sun. So this is sun, that's Earth. And this is December 21 or 23, I think, I don't remember, right? This is June 21, June 23, either December or January, right? These 2 points. And these 2 points here, right at the center here, these 2 points here is March 21st and September 21st. That's the equinox. Right? What do you call this? When the days are the longest, right? Here the days are the longest, days are the shortest. And here, all over the world, days are...
I think it is solstice and equinox.
Yeah, these 2 are the equinox. Okay, these 2 points are the equinox.
Mm-hmm. The other ones are
And the
solstices.
equinox has this feature that everywhere on Earth, the length of the day is the same, wherever you are on Earth on that particular day. The length of the day, the sunset and sunrise, the length, distance between them, or time difference between them is exactly the same. Those are these 2 points. But here's a question for you. We have R naught sitting everywhere, right? This whole problem, we have a natural set of units, that's R naught, correct? Where is R naught in this diagram? Is the question clear?
The projection of R on x-axis.
Where?
He's saying that the projection of what you use to get the angle on the
No, R naught.
axis.
R naught is a special point. R naught is a scale, right? It's a length. It's a very special length that sets your units. Right? We are measuring distance in R naught, at least in this work, at least on whatever we have written on the board. So it's good to know where is that distance, right? Is it this distance? Is it this distance? Is it this distance? This distance? This distance? Where is R naught?
Between the center and R max.
Between center and R max.
The center of let's say the origin of x and y axis. Yeah, that point between those 2 points.
No, that will be R naught over 2, right? 1 minus E.
So it's not at the origin of...
That will be A over 2, right? That will be A over 2. That's not.
I don't know. Is it a point? Or is it a distance?
Just go back to your equations. That's your equation, right?
Mm-hmm.
How would you define your R naught there? At what point does R naught come out? That's your solution, right?
Mm-hmm.
For what phi is R equal to R naught?
0.
Try again.
When,
Pi over 2.
Pi over 2,
yep, okay,
correct?
yep.
So now come back to this diagram and tell me where is R naught?
On y-axis.
This one?
I don't know. It could be anywhere. Between the origin and minor length, of course.
Between the origin, this is your
The origin of xy axis.
Oh, here, between the
Yes.
origin and here?
Yeah, somewhere between that point and.
Tell me again. R radius is exactly equal to R naught at phi equal to pi by 2. Where is phi equal to pi by 2 in this orbit? Remember, the orbit is determined by phi equal to 0, right? Phi equal to pi. Where is pi by 2? That's your angle.
What?
Make it by 2. So that's somewhere here.
So when R is equal to R minimum, phi is equal to 0,
When
right?
phi is equal to pi by 2, R is exactly R naught. That's this distance. Which we gave it a lot of special, we set a scale using that. Okay? That's your R naught. In analytic work, that played a big role, but that's not very relevant as far as this ellipse goes. But it's nice to ask, on which date is R exactly equal to R naught? Right? This is March,
July 31st.
September 23rd, right? So when does this fall? That's an exercise for you guys.
July.
No, you cannot guess it like that. Okay. Okay, and again, just for you to explore, I don't have an exact answer either. If you can get a nice way to do that, that's good, but it should be doable.
Pi measures time, right? So if we
Pi
divide
measures time,
365
exactly.
and a quarter
Exactly.
by
Exactly.
2 pi, and then solve for pi over 2.
Yeah, but that integral has R in it, so that you have to substitute this. So remember, mu. So that's your angular momentum, right? Oh, can I? I'm not pointing. That's your angular momentum, but you have to substitute the equation of the ellipse itself into that.
Do we have to in order to determine where R naught, at what
What the
time of
time
year
is,
R?
yeah. Yes, exactly. Or I think you might have to, but I'm not sure. Okay. Maybe there's easier ways. I would think there is an elliptic integral that will come in.
I was just thinking.
Maybe there are easier ways. I don't want to.
How much time of the year passes between the solstice and pi over 2?
That's correct. That's exactly.
I don't think you need to.
Actually, when it is pi over 2, you're right. Things get simpler. Elliptic integrals are doable when it is exactly pi over 2. No, you might be right. It might be very easy.
Well, I guess I wasn't even thinking about solving an integral, but
Like that's what you're suggesting, right? From what I could gather, I think what.
Well, what I was saying was you take 365 days, and you put that into 2 pi radians, and then you determine how many days pi over 2 is, and then you add that to the summer solstice or whatever it is.
It's not linear, right? Only if it is linear, you can do that ratio problem.
Okay.
That's weighted by R square then. Right?
Okay.
Yeah, but that's pretty much the same argument, just that you have to weight it a little more or less.
Okay.
And yeah, if you guys can calculate that, it's a sort of extra credit problem. Again, remember there is no extra credit in the sense of submission now, because I don't want to deal with submissions by emails.
We can't still submit at the end.
Yeah, so this particular problem, if you get me the date of R0, exact date, that's amounts to a lot of extra credit. How about it?
Okay.
Not just one extra credit. I have earlier in the, I think the first time I taught this, I gave it as a problem that if you can calculate this exact date, I will boost your grade by 1. So if you get a B, you get an A. Okay. So show me your good. Show me how much work you have put in. If you show it as a trivial way, then that's different. Like, do some thought on this. Okay. But you gave the right point, Moses. I think that's the way to proceed. I would say. Is that clear, the discussion? So again, if you can tell me on which date R0 falls, this time I'll be impressed. So let me stick to that. But I'll surely reward you in some way. But let me not commit to saying that I will boost your grade.
And we can't just look it up on the internet.
You can look it up. I don't think it's there.
Yeah.
I don't think it's there, but again, you never know. Yeah, I'm not sure. You can look it up, yes.
Well, yeah, but if we looked it up, then that would
don't
wouldn't be worth the extra credit.
Don't cut and paste. That's my only thing. Do some creative contribution in whatever is there. Or here is how usually I say in research problems: refer to the internet, refer to the literature, but better. Prove on it. Give some contribution from you. There's nothing wrong in using the literature, but do it better than the literature.
Okay.
Then it's worth rewarding. But don't cut and paste. I think you guys are not doing it, so that's why I'm telling you that. Yeah, I think it will be nice. Maybe it is trivial. Yeah.
Sounds good.
Yeah. Okay. Reasonable? I think, yeah, this sort of covers what I wanted to do the parabola also today, but I think Jordan has to leave, so I think we'll let him go.
But you can continue to do it if you want. I'll just look at it afterwards. Okay.
No, it's already half an hour more.
I think
shouldn't.
It would help if we started class at 9:35 instead of
I know.
instead of 9:50 or whatever.
Yeah, I know. But then I also let it happen because I thought.
Well, yeah, we weren't all on.
Relax and. Yeah, we'll see. Yeah. But we're meeting on Tuesday, so that should be good. So maybe based on what question I ask. Oh, how about this? Parabola is an exam question. How about that? I will set the problem.
Okay.
Like exactly based on whatever we have done here, the same arguments, we will use it for e is equal to 0. And we'll show that. I will guide you through it. I'll design the problem. Yeah, that's, I think, good. Because hyperbola becomes a little more work, but parabola comes out almost immediately. Okay. Good. Okay, that's a good, I have one more question in my head. Okay.
Cool.
Okay.
So are they gonna be 4 questions?
I think, yeah, 4 questions, not 5. 4.
Okay.
Usually, I think graduate level, I try to be 3 or 4. Like, usually my goal is 3 problems, 2 problems from immediate, 1 problem challenging, and 1 some reading exercise. That's what I put for graduate level. I go and read some article and explore on that. So I keep it open. But this time I may not have that. Yeah. Or I will design the fifth problem as determining R naught. Now that Moses has kind of quantified it to a certain extent, I think that's the right procedure, and maybe set it up a little so that you guys can do it. Or I think I should leave it open. You guys do whatever you want and give me the date for R naught. I'll leave it very open and maybe do something. Yeah, I'll decide upon that. Wait for it on Tuesday. Okay. Good.
Okay.
Yeah. Okay. Good job. Any other comments? Questions?
I still think it's in July though.
Oh, it might be. No, it might be, but
Cause I know July 31st has some important significance. It could be that.
oh, I am not even sure if this is discussed so much in literature. I'm not sure if this is discussed
Okay.
in literature, or this is any special. Like these points are special.
Mm-hmm.
It's just is based on our choice of units. It's a very, would the right word be mundane? Kind of very human, very human dependent. Not a, nature did not pick it, I think. So, but again, maybe there is something to it. So again, that's what I would like to know. How about that? What is the significance of that point? Maybe that is a better. When does it come? First, we begin by saying that that is the day, and then ask, is it talked about in the literature? If it is not, you guys should write a small 3-line article on it and say that this is that point.
Maybe
I mean,
it was significant for the ancient Egyptians.
yes, I mean, if it is not, I mean, that's a, like, this is our mathematically, that makes sense. So, I don't know if it is significant or not,
Right.
physically speaking.
So do we consider January 1st is at pi = 0?
Don't ask me. Do ask
Yeah, it's
do,
going to
do
be a one of
anything.
the solstices.
This is not.
Could you solve this problem easier because just using geometry,
Probably.
saying
I don't
that the Earth's axis on equinox is pointing directly towards the sun. Therefore, the
That's on the
You're
solstice,
saying-
not on the equinox.
the axis of the Earth on equinox, the axis, the like equinox,
Oh, I see.
on
Okay.
equinox, the axis
This
points
is-
directly to the sun. So on equinox, if you look on the ellipse he has there, Moses,
Yeah.
there's a tilt to the Earth. And equinox is when the axis of the Earth points directly towards the sun.
Okay.
So
I thought that happened on the summer and winter solstices because like the northern hemisphere is tilted away in winter and tilted towards. Okay.
nope, it should be June. I think June 21st is when the axis is pointed directly at the sun. Pretty sure. Stop.
In June, probably not.
No.
June
June-
21st is the.
No, probably you're meaning the September and March.
Yeah, that's what I meant. Yeah.
So I think your point is, Jordan, that
Using the axis, can you just use geometry?
probably, see, that's what I'm trying to say. I haven't worked on it too much. I've asked this question, but I have myself not worked on it. But probably because I didn't have a better way to say it is that I haven't got a nice idea on
Okay.
it, and I was never motivated to do that. But there might be very simple ways of doing it. Simple doesn't mean that it's wrong or trivial.
Okay.
So first do it however you can. Do it one way at least.
Okay.
And then we will see if it is done in the literature at all or not. I don't know again. Like for me, this is just choice of units. It's a natural units you choose, correct? And that's somewhere here. And again, I mean, one would think that people have thought about it, but I never heard of it in astronomy or anything that we never talked about this point, right? Or at least in my simple, very little reading that I've done in this context. Okay. Please.
Okay. Mm-hmm.
So the point is, I don't know. So you're completely free to do whatever you want. Tell me something impressive. Okay.
Do my best.
Yeah, again, it's okay. If you, even if you don't do it, it's perfectly fine. Is that clear enough?
Yeah.
Mm-hmm.
It might be too trivial. It might be too hard. As a typical research problem is, you don't know what it is. Okay.
Cool.
Good. Okay.
All right, guys. Well,
Okay. Enjoy, guys.
Thank you.
Thank you.
see you later.
Goodbye.
Oh, be safe from the cops.
Oh, thank you. Yeah, no, they left.
That's okay.
All right, see ya.
Is it, why are they in your neighborhood?
I don't know what they were up to. There were a couple of them.
Maybe they were looking for some,
Something's afoot.
maybe they're looking for some, meth labs.
It's possible.
Yeah, Missouri is pretty known for meth labs.
Yeah, they're around. Yep, I don't know. I don't know. What time do you guys have E&M?
12:30.
Oh, okay.
I need to work a little on that.
Gotcha. I guess I get to take that
Questions?
next semester.
Oh, yeah. I think next, I don't know, the times keep changing from semester to semester. So it's not, if you're asking for the purpose that, is it going to be at 12:30? I'm not sure.
Oh, no, I don't know. It doesn't matter. I was just wondering.
Yeah. So fall, you will probably take E&M 1 and then.
Yeah.
It is not very different from undergraduate E&M, right?
Since I teach it, yes. It's very similar since I am the same person who teaches it. But I make it very, undergraduate is way milder.
Yeah.
So.
Do you use Griffiths?
Yes, that's what I use. Yeah.
Okay, cool.
For undergraduate or graduate? Did you mean for graduate or undergraduate?
Undergraduate is Griffith. Yeah.
You use it at graduate level too?
No, graduate level is I use Stringer.
Okay.
Milton and Stringer, so there's a book by him. Yeah.
Gotcha.
But I use the same contents, but I make it available in the context of Griffith. I think that's the way to put it. Yeah.
Okay.
Don't strictly follow Griffith.
Mm-hmm.
Pretty much like this course, I don't strictly follow Goldstein, even though it's a textbook.
Yeah.
But I don't strictly follow it. Yeah. So.
Cool.
Yeah.
All right.
E&M is a little more challenging the way more than this course, I think. Usually that's how students view. Yeah.
Yeah. Yeah, I'm not surprised. Cool.
Yes, Avinash, you were saying something?
No, I was just gonna say good day.
Yeah.
Yes, thank you.
We don't have breakfast.
Okay.
Bye.
See ya.